Starship Flight 12 failed, and the data already shows exactly why. It wasn't the booster, it wasn't the fuel, it was a few milliseconds that sent a $3 billion rocket spinning out of control. Here's what happened. During hot staging, 2 Raptor vacuum engines on the upper stage fired out of sequence. That tiny timing gap kicked the super heavy booster sideways instead of cleanly upward towards space. The result? The booster flipped uncontrolled, exhaust slammed directly into its own grid fin, and the whole separation became a disaster on live TV, watched by millions. The crazy part? If those engines had fired in the correct order, none of that damage would have happened. The booster was never the problem. So what exactly went wrong? And what is SpaceX changing for Flight 13? Stay with me. Let's go back to that exact moment. Flight 12, hot staging sequence. The most critical 10 seconds in the entire mission. Everything looked perfect on the outside. The rocket was climbing. The numbers were good. Millions of people were watching live. And then, it happened. The super heavy booster, weighing over 200 metric tons, suddenly lurched sideways. Not backward, not upward, sideways, like a 70-meter skyscraper getting slapped by an invisible hand and spinning out of control at the edge of space. Within seconds, the booster was tumbling. Exhaust from the upper stage engines was blasting directly into its own grid fin. The structural forces involved were catastrophic, and the whole world watched it happen in real time. Now here's what nobody was talking about immediately after. The SpaceX commentator, Dan Hewitt, had literally just described, seconds before the failure, exactly how this was supposed to work. He said the 3 Raptor vacuum engines on the upper stage would ignite first, almost simultaneously. Then one central sea-level engine would fire, giving the booster a clean kick in the correct direction. Then the other 2 sea-level engines would follow. That was the plan. Clean, precise, choreographed down to milliseconds. What actually happened was the complete opposite of that. The answer to why Flight 12 failed was hiding in plain sight, in the engine ignition data streaming live on screen during the broadcast. Most people missed it entirely, but once you see it, you cannot unsee it. So what exactly did that data show, and why did it matter so much? This is where the real story begins. The physics of hot staging. Why this is so insanely hard. Before we go deeper, you need to understand what SpaceX was actually trying to do here. Because hot staging is not a normal thing. It is one of the most violent, precise, and frankly insane maneuvers ever attempted in rocket history. Here is the simplest way to think about it. Picture 2 trains connected together, moving at 7,500 kilometers per hour. While both trains are still moving at full speed, you need to separate them, but also light the engine on the front train at the exact same moment, using the exhaust from that engine to push the rear train backward and away. All of this needs to happen in less than 10 seconds, with millisecond precision, at the edge of space, where there is no air, no gravity assistance, and no second chances. That is hot staging. And it gets even more complicated with version 3. The new Super Heavy booster has only 3 grid fins instead of 4. And one of those fins sits right at the bottom center of the booster. That placement changes everything. On flights 9, 10, and 11, the Starship stack flew in the standard orientation. Heat shield belly pointing down toward Earth. The upper stage exhaust naturally pushed the booster upward and away in the correct direction. Beautiful, controlled separations. Flight 12 was completely different. Flight 12 flew inverted. The heat shield belly was pointing up toward space. The leeward side angled toward the ground. This was intentional, because without the inverted orientation, that central bottom grid fin would have been directly in the path of the upper stage exhaust, getting destroyed instantly. So SpaceX flipped the entire stack orientation, which meant the correct flip direction for the booster was now reversed compared to every previous flight. Every flight before this, the booster flipped one way. Now it needed to flip the exact opposite way. New engines, new fin configuration, inverted orientation, all happening simultaneously during the most dangerous 10 seconds of the flight. The margin for error was almost zero, and that margin is exactly where things fell apart. The engine sequence that changed everything. Now we get to the core of the failure. This is the part that most coverage missed entirely. When you slow down the telemetry data from Flight 12, frame by frame, you can see exactly what happened. Here is what was supposed to happen. All three Raptor vacuum engines were supposed to ignite simultaneously. That simultaneous ignition would create a balanced, even push on the top dome of the booster, straight backward, setting up the perfect conditions for the sea-level engine to then kick the booster cleanly upward towards space. Here is what actually happened. The bottom Raptor vacuum engine on the windward side of the ship ignited first. Then the left Raptor vacuum engine fired. Then the first sea-level engine lit up. And finally, late, the third Raptor vacuum engine came online, followed by the remaining two sea-level engines. The firing gap between these engines was measured in milliseconds. But at the scale of forces involved in rocket propulsion, that gap is everything. When the bottom Raptor vacuum engine fired first, it created an asymmetric force on the booster's dome. Instead of an even push straight back, the booster got a push biased downward and to one side. When the left engine followed, also before the right one, it added another lateral force component. The result was like pushing a spinning top from two unequal sides at slightly different times. Instead of spinning cleanly, it wobbled. It lurched, and by the time all engines were firing, the booster was already moving in the wrong direction and accelerating. Then something made it dramatically worse. As the booster moved off-axis, the upper stage exhaust started hitting the grid fin on the right side of the booster. That exhaust impact acted like an unplanned thruster. It accelerated the spin further, creating a feedback loop of forces that nobody had designed for and nobody could stop. Within seconds, the booster was completely out of control. And here is the brutal irony. The fin that got hit, the fin that made everything worse, was one of only 3 on the booster. On the version 2 design, 4 fins meant losing one was bad but recoverable. With only 3 fins, losing effective control of one is catastrophic. SpaceX reduced the fin count to save weight. It was the right engineering decision for normal operations. In this failure scenario, that decision amplified the consequences significantly. So was this a hardware problem, a software problem, or something else entirely? The answer might surprise you. Who is really to blame, the booster or the ship? This is the question debated endlessly since Flight 12, and most people have been pointing at the wrong thing. The immediate visual was dramatic. The booster exploded. The booster tumbled. The booster was destroyed. So the natural assumption was that something was wrong with the Super Heavy itself. There were legitimate concerns about the booster design too. When Booster 18 was scrapped after a rupture at the test site, it gave engineers, and the public, an unprecedented look inside the version 3 Super Heavy. And what they found was striking. The version 2 booster had slosh baffles inside its propellant tanks. Think of them like dividers inside the tank, internal structures that slow down the violent movement of liquid propellant during sharp maneuvers. Without them, thousands of liters of super-chilled liquid oxygen and methane can surge through the tank, slamming into pipes, valves, and structural components with enormous force. The version 3 booster had no visible slosh baffles. When the booster lurched off-axis, pushed by the asymmetric engine ignition, all of that propellant slammed to one side. Metal structures hit forces they were never designed to handle. Things broke. The booster came apart. But here is the critical distinction that changes everything. If the booster had flipped in the correct direction, the direction it was designed for, those sloshing forces would have been completely different. The propellant would have moved in the expected way. The structural loads would have been within design limits. The booster did not fail, and then flip wrong. It flipped wrong, and then failed. The root cause was upstream. It was the engine ignition sequence on the upper stage Starship. And the fact that SpaceX's primary focus after Flight 12 has been on the upper stage ship, not the booster, speaks volumes. The The data points in one direction, and SpaceX's test choices confirm it indirectly. But this raises the next question. If the engine sequence caused all of this, why did it happen in the first place? Was it a software command that went wrong? A sensor failure? A valve that opened a fraction too slow? SpaceX has not told us exactly. And that silence is itself significant. What SpaceX is actually fixing and what they are not saying. After Flight 12, Ship 40, the vehicle designated for Flight 13, began its testing campaign. And the way that campaign unfolded tells us exactly where SpaceX's attention is focused. Ship 40 rolled out to the Massey's test site. It passed an igniter test first, a small controlled ignition to verify the system. Then, 24 hours later, it performed its first static fire using a single, brand-new Raptor 3 engine, a sea-level engine, running for approximately 15 seconds. SpaceX described this as full duration, suggesting it was simulating the in-space deorbit burn the upper stage performs in orbit. Think about what that means. The very first test on Ship 40 was one engine, one specific burn profile. Carefully isolated, carefully controlled. That is not how you test a vehicle you are confident in. That is how you test a vehicle where you are validating very specific behavior in a very specific sequence. The next logical step would have been a full 6-engine static fire. That did not happen. Ship 40 was rolled back to Mega Bay 2 without completing the full engine test suite. Something showed up in that single engine data that needed further attention. SpaceX has not said what. But given everything we know about Flight 12, the most logical explanation is engine sequencing, timing, ignition behavior, or valve response that needs adjustment before they can proceed. On the booster side, Booster 19 has been sitting inside the Mega Bay waiting for its own static fire campaign. Water deluge testing at Pad 2 was still ongoing, suggesting SpaceX was refining the pad systems before rolling the booster out. And there is one more detail on Booster 19 worth paying close attention to. Photographs of Booster 19's forward dome show additional steel plating in specific areas. Not everywhere. In specific locations that correspond to where the upper stage exhaust spends the most time during a correct hot staging flip. That is targeted reinforcement. That is an engineer saying, we know exactly which parts of this dome take the hardest hit, and we are protecting those specific spots without adding mass anywhere else. Because mass is the enemy of performance. Every extra kilogram on the booster is a kilogram that cannot go to orbit. SpaceX is walking the tightest possible line between structural protection and payload capacity. This is what precise engineering looks like at the frontier. Not protecting everything, protecting exactly what needs it. Which raises the harder question, if SpaceX understands the failure mode this precisely, why did they not catch the engine sequencing issue before Flight 12? What does that tell us about the limits of simulation and ground testing? Milliseconds at the edge of physics. There is a bigger story here that goes beyond Flight 12 specifically. The entire hot staging sequence, from upper stage engine ignition to clean booster separation moving in the correct direction, takes less than 10 seconds. Within those 10 seconds, you have multiple engine ignitions, a physical separation event, a directional flip driven by exhaust impingement on a curved dome, and the beginning of independent flight for both vehicles. Every single one of those events is interdependent. If one is off by milliseconds, everything downstream changes, and there is something SpaceX cannot fully simulate on the ground. You can test individual engines, you can test separation mechanisms, you can test control software in isolation, but you cannot fully replicate the exact aerodynamic and thermodynamic environment of hot staging at altitude, with real propellant loading, real vehicle mass, real atmospheric conditions, all happening simultaneously. Some things can only be learned by flying. Flight 12 was SpaceX learning one of those things. The question now is, have they learned it completely? Or will Flight 13 reveal another layer of complexity that only becomes visible at full scale, at altitude, with everything running at once? That is not a pessimistic question. It is an honest one. And it is the question that makes every Starship flight so compelling to watch. The bigger picture, why this matters far beyond SpaceX. There is one more layer to this story that almost nobody is talking about. The Raptor 3 is a fundamentally different machine from the Raptor 2 that powered earlier Starship flights. More powerful, more efficient, more compact. A generational leap, not an incremental improvement. But more power creates new sensitivity. In hot staging, a more powerful engine means more exhaust force impinging on the booster dome during separation. More force means smaller tolerances. If engines fire slightly out of sequence, the resulting asymmetric force is proportionally larger than it would have been with less powerful engines. The Raptor 3's power is both the solution and part of the problem. It gives Starship a dramatically better thrust-to-weight ratio and allows far more mass to reach orbit. But it also makes the millisecond timing of hot staging more critical than ever before. SpaceX is not just fixing a sequencing bug. They are recalibrating the entire hot staging system for a more powerful engine regime. And this connects directly to the version 3 design philosophy. The version 2 vehicle's dry mass was much too heavy. The entire version 3 redesign was driven by reducing that mass while increasing thrust. Removing slosh baffles. A deliberate weight-saving choice. Reducing from 4 grid fins to 3. New Raptor 3 engines. Every decision made in service of that goal. That means SpaceX made a calculated bet. They stripped weight, including certain safety margins, because they were confident in their ability to control the vehicle precisely enough that those margins would not be needed. Flight 12 tested that bet. And the test revealed the confidence was slightly premature. Not wrong in concept, premature in execution. The fix is not to rebuild everything with added margins. The fix is to get the precision right. Nail the engine sequencing. Make the booster flip exactly as designed. Let the structure handle the forces it was built for. Let the targeted reinforcements on Booster 19 provide the additional margin the design needs at the dome. SpaceX has been through this before. Falcon 9 went from a concept nobody believed in to a booster reflown 33 times in a single program. That journey had failures, redesigns, moments where the whole concept seemed impossible. The process is the same now. The scale is just far bigger. Flight 13 is the next step on that journey. The engine sequencing will be different. The ignition timing of those Raptor vacuum engines will have been analyzed, adjusted, and validated through every ground test possible before the vehicle leaves the pad. Will it be enough? Will Flight 13 nail the hot staging and send both vehicles to their intended destinations? That is the only question that matters right now, and the answer is coming soon. That is the full picture of what brought down Flight 12. Not a booster failure, a millisecond timing error, and everything that followed from it. If this analysis gave you something new, hit like, share it, and subscribe to the Space Brief. Drop your thoughts in the comments. I read every one. Thanks for watching.